everyone, welcome back to class. In today's video, we are going to be talking three-dimensional trigonometry. And in particular, we're going to be looking at situations where we have idea angles of elevation and angles of depression that come up in those diagrams. We want to make sure that we use our tools correctly. And because these diagrams tend to be especially tricky for a lot of students in that they present a 3D situation on paper, which some students find a bit difficult to see. I'm going to be showing you how you can best solve those questions by separating the diagrams into smaller parts and using the tools that you need to use to solve them correctly. So here we have a situation where we have a lamp post that is seated on a flat surface. Now, this flat surface in your diagrams would be represented something like this flat surface here. Sometimes it will not have any borders. It will just be placed there as a flat surface with just a vertical line. So all that you'll be seeing is triangles on your diagram. Triangles like that. But in reality, when you look at it, it's actually something like this. It's just that when you draw it on paper, it's a bit difficult to get it to look like these. So notice something. Whenever you have a vertical post on a flat surface, every line that you draw to the base of that post will make a right angle with that line. So any line that you draw will make a right angle with that. And also coming into play are angles of elevation and depression. Remember that an angle of elevation looks down on something and an angle of elevation looks up at something. So here you would have your angle of depression of something looking down. This is your angle of depression. And here you would have your angle of elevation, and the angle of elevation looks up, the angle of depression looks down. But because these two lines are parallel, then we have that this angle of elevation is the same size as that angle of depression due to the Z angle or the alternate angle situation here. So two things to remember: the Z angle comes up a lot, and any line that you draw on the plane, on the flat surface to the base of your pole will create a right angle. So right angles will be plenty in these once they touch the post. Let's look at the first question that we have here. The diagram shows a vertical pole PL. So this is your pole PL, and PL is standing on flat ground or a flat surface, standing on a horizontal plane. That's what it means, a flat surface. And we are given some measurements. The angle of elevation of P measured from K is 28. So we have to put in our 28 here. We have two distances. KL is 15. KL, this is KL here. That's 15. And also we have LM is 19. And so we can put in that. And we also have an angle here that's 115 degrees. That's already given and drawn into the diagram. So we have copied our diagram. Well, you would have copied it in your notebook or wherever on your question paper and you have answered it. Make sure that you put in the information that you get correctly. That's important. You don't want to put the information in the wrong place. And then we're going to do some calculations. So first we're looking at PL. Now where is PL? PL is this line. And PL, as you notice, is in this triangle PLK. It's also in this triangle PLM. This triangle PLK, however, has a lot more information in there. And so we're going to separate that triangle PLK and use it to answer our question. There's our right angle. Remember, right angle goes there, right angle goes here as well. So we have 15, we have 28, and this is the side PL that we want to find. We are told to calculate it correct to two significant figures. Now, you notice here that PL is the opposite side. It's opposite to the angle. And this side KL here is the adjacent side, and opposite and adjacent makes tangent. So we say the tangent of the angle 28 is equal to PL over 15. And once you cross multiply this, you will realize that PL is equal to 15 times the tangent of 28. That turns out to be 7.98 once you plug it in your calculator. But because we're asked to write it to two significant figures, we end up just having 8.0 meters. Because two significant figures there, we'd end up rounding up everything to 8 meters. So we have found our PL. Next, we need to find our KM. KM is in this triangle at the base. So we have to separate that triangle there, or not have to, but it makes sense to separate it. So we have K, we have L, M here, and we have L at the corner, and 115 degrees. Now this side is 15, this side is 19, and as you draw it up, you'll realize that the only way to get Km here is to use the cosine rule. So we can use the cosine rule to find Km by saying Km square is equal to 15 square plus 19 square minus 2 times 15 times 19 cos 115. And once you punch that in your calculator, you end up with 827 approximately. And finding the root of that gives us approximately 29 meters. Please pause the video, do the calculation, and check it yourself to make sure that you have arrive at the same answer here. So this is part B, this is part A, this is part B, and now we go to part C. Part C says we are to find the angle of elevation of P from M. Remember in this diagram here, we found this side to be 8. So we want the angle of elevation of P measured from M, which tells us that we're using this triangle over here. Let's just take out that triangle a bit and look at it in terms of the numbers and stuff we have on it. So here we have 19. Here we have 8 and our right angle as well. And we want the angle of elevation of P measured from M, which tells us that we need this angle. And because we want that angle, we have 8 and 19 again, which are tangent. So we can say the tangent of the angle PML is equal to 8 over 19. And we want the angle, so we use the inverse tan. PML is therefore equal to tan inverse of 8 over 19. And when you work that out, you end up with 36 degrees. So it helps to split the diagram into pieces. And once you split them in pieces, you begin to see exactly what you need to calculate and how you need to calculate it. Let's look at our next question. Our next question is, we have a TF, which is a flagpole, and that flagpole is on a horizontal plane. It's vertical and it's on a horizontal plane. Two ropes, TP and TM. TP and TM are attached to the top of the pole, and there are two angles of depression that are not shown. So let's draw in one of them just to let you see exactly what is going on. The angle of depression of M and P, that's M and P, those 2 points. So something is up here looking down at M and P from T are 60 and 40. So if we should draw in the angle of depression of P from T, we would end up with an angle of 40 degrees. And notice something now. Because of this Z angle here, we're going to have this angle, this 40 degrees, is going to be reflected down here because those two angles are alternate to each other. By that same reasoning, this angle over here is going to be 60 degrees. And angle PFM, which is on the horizontal plane, is 45 degrees. Let me just put that in a different color. 45 degrees here. All right, that one is on the horizontal plane, drawn flat. So we're told to find PF. Let's see if we can find PF. PF is this side of the triangle, and we can use a triangle TPF. So let's separate triangle TPF. Let's see what's going on here. This is P, this is F, this is T. All right, there's our right angle, and there's our 40 degrees. And of course, this side is 15 meters. Now, we can find PF easily now because we see that this is a right angle triangle. This is the adjacent side, this is the hypotenuse, and therefore we use the cosine. So we say the cosine of 40 is PF over 15, which tells us that PF is equal to 15 times the cosine of 40, and that gives us 11.5 meters. The next side to find is MP. MP is in the triangle on the horizontal plane. So let's separate that triangle by drawing the triangle. There it is. This is M, this is P, and this is F. The information we have for this triangle is that this angle here is 45, and we just calculated PF. PF is 11.5. So we know that. What we also know that we must calculate PM, but we need some more information. If we knew this side, for example, we could use the cosine rule to find it because we don't know the other angles there. If we knew another angle here, we could probably use the sine rule to find it, but we cannot use it because there is no other information given. But what we do know from the other triangle, the other depression angle that was given, that if we take out this triangle, TMF, let's take out TMF and look at it. That triangle, TMF. Now, FM here and T, and we know that this angle here is 60, and this side is 11. And because we know that, we can use it to calculate the length of FM here. Because FM, we can use the same principle up here by applying the cosine rule. Applying the cosine rule to the diagram tells us that, not the cosine rule, the cost ratio, where we have that the cosine of 60 will be equal to FM over 11, which tells us that FM is equal to 11 times the cosine of 60, and that should give us 5.5. So this is 5.5, and now that we know it, 5.5, we can go ahead and use the cosine rule to calculate the length of our PM. So by using the cosine rule, MP square would be equal to 11.5. Notice you have the two sides there and the angle between. That is the condition for using the cosine rule. 11.5 square plus 5.5 square minus 2 times 11.5 times 5.5 times the cosine of the angle given. That's 45. When you do all that calculation, it should give you approximately 73. And once you find the square root of 73, you would end up with 8.5 meters, which would be the length of PM. So again, it's very, very useful to remember the idea that the depression lines extend in that direction and depression angles are equal to elevation angles in the same diagram when you draw them like that. And to separate the pieces, separate the triangles and do the calculations differently. That will be a major help in understanding how these questions work out. The next question has to do with this diagram. Notice that we have some information in there. We have a point, we have a tower FT, and there's an antenna on the top of the tower, mounted on top of the tower, and we have some information to put into the diagram. So the question says copy and label the diagram showing this information here, distance, angles, and the right angles. So this FP, if you're looking at it in a real situation, would be like a house, and you have like a TV antenna on top of your house. It's something like that. So we have our TF, it's vertical, it's standing on a flat plane, and this distance from P to F here is 28. So we can put in our 28. And also the angle of elevation of T and W from P are 40. So 40 is the smaller one, it goes here. And the bigger one is 28 is 54. It goes here. So the 54 is measured from this line to this line, and the 40 is measured from this line to this line. It's important that we see that. And the right angle, of course, is here, because any line that you draw to that vertical, as long as it's standing on the horizontal there, is going to give us a 90-degree angle. So we have put in our information, and now we're asked to find the length of TW. Now TW is the antenna. So let's look at this side over here. FW, this long side FW. FW is equal to two smaller lines. It's equal to FT. When you add FT to TW, you get the complete line FW. So if we want to find TW, we can say, all right, then TW is equal to, by just rearranging this equation, TW would be equal to FW minus FT. FW minus FT would give us TW. And so what we need to do now is to separate our triangles and do our calculations. So if we separate our triangles, PTF, let's draw that one. Let's draw the bigger one first, PWF. PWF, this is our P, that's our F, that's our W. So we're doing the big part first. This is 28, and our angle there is here is 54 degrees. So we can look at it here. FW is the opposite side. Here is the adjacent side. So we're using the tangent ratio. So we can say FW, the tangent rather of 54, is equal to FW or WF over 28. And by cross multiplying, we see that WF is equal to 28 times the tangent of 54. And 28 times the tangent of 54 gives us 38.5 meters. Again, remember to put your calculator in degree mode. It's important to do that when you're working with angles in trigonometry. All right, now that we have that, we need to find the smaller one. We need to find FT. So let's separate that smaller triangle FT. Please remember to pause the video and do the workout so that you can see it. This is our 40 degrees. 40 degrees. And we have our 28 here. And now we are finding TF. So in finding TF, this is opposite, this is adjacent. We're going to use the same tangent. So the tangent of 40 is equal to TF over 28. Cross multiplying here as we did before, we end up with 28 tan 40, and that is equal to TF. And that gives us approximately 23.5 meters. So now we have our two numbers. We have FW and we have FT. So to finish our calculation in finding TW, TW would be equal to FW, which is 38.5, minus FT, which is 23.5. And doing that calculation there gives us that TW is equal to 15 meters. So the height of the antenna here is 15 meters. Again, by separating your diagrams, make sure you put in your information correctly. Separate the diagrams, work them separately, break it down into smaller pieces, and working it out, you realize that the problem is not as difficult as it looked when you started. And we're going to look at our final question now, which is another case where we have a diagram with some angle of elevation just drawn in a different way. The angle above, the diagram above shows, and they're not drawn to scale here is very important, so that you cannot use your ruler or your protractor to measure angles or to measure distances. You have to use the trigonometric calculations to do it. So just in case that you think that it's drawn to scale and you want to use your ruler to measure it, it cannot be done because they're not drawn to scale. So you have to use the trigonometry tools. All right, so let's get to this question. The diagram shows the angle of elevation of T, the top of a vertical mast. A mast is something like a flagpole. You raise a flag on. And from the points P and Q, these 2 points are on the same horizontal plane as R, which means that they're all in a flat plane and probably in a straight line. All right, exactly in a straight line. We're told that PQ is 25 and the angles TPQ and TQR, there they are, they're already in the diagram, are 53.1 and 64.6 degrees. Now, the first thing we're supposed to do is to show that the length of QT, that's this side here, is equal to 100 meters. How can we do that? First, I am going to separate the diagram. Look at this triangle here. We want to show that QT is 100 meters. So we want QT. So first thing we want, there are no measurements over here for us to use. The only measurement here relates to this part of the triangle. So let me separate that part of the triangle so we can have a better look at it. All right, so let's have that. This is our triangle here. Okay, this is P, this is Q, and this is T up here. Now, what do we know? We know that this is 53.1, this angle. And we know that this angle over here is 64.6 degrees. Yes? And we know that this side is 25. This is not a right angle triangle, so you should not be looking to use sine or cosine or tangent. Rather, we have to be looking at whether we can apply the sine rule or the cosine rule. It looks as if we can apply the sine rule in this case if we can say 25 over the sine of this angle is equal to this side QT, which we need over the sine of 53.1. But to find this angle here, we first need to find this angle here. But notice here that this angle and this angle right here would make a straight angle. And so if we take away 64, a straight angle measures 180 degrees. So 180 degrees minus 64.6 degrees gives us approximately 115.4. So this angle here is 115.4 degrees. And when you add 53.1 to 115.4, and remember that angles in a triangle add up to 180 degrees, and this angle here will give you 11.5 degrees. So this angle is 11.5 degrees. This angle here is 53.1, and this angle here is 115. You could also find this angle by subtracting 53.1 from 64.6, if you know about that theorem that these two angles add up to give you the external angle here. But once you found them, then you realize that now we can apply the sine rule to this triangle to find the length of QT. Applying the sine rule would tell us that QT over the sine of 53.1 would be equal to 25 over the sine of 11.5. And cross multiplying this gives us QT times sine of 11.5 is equal to 25 sine 53.1, which tells us that in the end, QT is going to be equal to 25 sine 53.1 divided by the sine of 11.5. And once you punch that in your calculator, you would get that QT is approximately 100 meters. It's actually 100.23, but when you round that off to the nearest meter, as the question says, you end up with 100 meters. So we have found part one, which is to find the length of QT. And now the second part is to find the height of the mast. That is, the height of the mast is this line here. How tall is that line? So let's look at that triangle. So what do we know about the triangle now? We know that this angle is 64.6 degrees. And we now know that this line is 100 degrees. But the thing about this question is, even if you didn't understand how to do part one, you should be able to do part two, because the question already gave you the length of the line here, QT, to be 100. So you could use your 100 to do the second part. Sometimes it happens that way in a question. Well, you would lose the marks for that one, but you can get the marks for this one, hence or otherwise. So here we are. We want to find the length of the mast. The mast is TR. We know this side is the hypotenuse, and this angle here, TR, is opposite to the 64.6. So we can safely use the sine ratio. So we can say the sine of 64.6 is equal to TR over 100, which tells us that TR is equal to 100 times the sine of 64.6. And once you do that calculation, punching in your numbers, you would get that TR is approximately equal to 90.3 meters. So the questions, 3D questions, appear like this often from time to time on your CSEC paper. Whenever they do, it's important to remember the tools that you need to use: sine, cosine, tangent, sine rule, cosine rule. They all come into play. And to remember that these vertical lines, any line that is drawn to them on the flat plane meets it at a right angle. And most importantly, it helps when you separate your diagrams and break down that problem into smaller pieces. And therefore, by working it in smaller pieces, you'll be better able to see through the calculation, to see through the diagram, and to be better able to solve these questions. Thank you very much for watching, and I hope that this would have brought some light to those kind of students who struggle with these kind of questions.